This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Wednesday, April 3rd, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss 2 lessons each week from the Math Map, Classical Conversations, that's been released for families with students in our Classical Conversations communities. And so I've been saying nearing the finishing line, and over the next week or two, everything's going to be available. So I just appreciate you guys hanging in with us. And Kirsty, of course, is up in New York City and is going to be working from phone, and Emma is around listening, but she's officially on maternity leave, and Christine and Julie are helping. So we're in the middle of all kinds of springtime growth and transitions. So I'm glad that you've all joined us to grow in your math abilities. Kirsty, what do we have today?
So I'm just sitting here looking out a window onto a New York street, watching all these umbrellas going by and thinking how they're just these perfect examples of rotational solids, which is so appropriate because today we're talking about calculus. We're going to look at differential calculus in lesson 25, and we're going to look at integral calculus in lesson 26. Now, Christine, if you want to look at the next slide. So we are here, lesson 25 and 26, and these are great examples of where we've chosen to name the lessons about what's going on in the lessons versus just using those calculus words that may be unfamiliar. We tried to find things that were more familiar and more descriptive. And so when we look at differential calculus, we're calling that the rate of change. In other words, right, how does something change? Is it a constant change or is it changing change? And calculus is the thing that really helps us to understand and analyze that. And then lesson 26 goes the other way, and we're still looking at change, but this time we're accumulating it. And so if you think of that idea of integral as being a whole, integrated, putting together, integral calculus is that idea of we're putting together pieces, and so we're accumulating that change. And so those are the titles that we're going to look at this week, which wraps up 4D and leaves us with 4 more weeks to talk about our imaginations. So I'm looking forward to the next couple of weeks as we finish up our quick tour through the Naturals Math Map.
So
next slide.
Does anybody got any questions? Are we gonna? No?
Yeah, did anybody have any questions before we jump in?
I'm sure you have lots of questions. You just don't know what they are yet. So go ahead.
Nothing in the chat. Nothing in the chat.
So I'm going to let you know that we're going to have the same basic questions on every page because we really want to help you see what we're doing in this lesson, because these are potentially challenging concepts that we're trying to introduce in very approachable ways. So let's go ahead and start by looking at our page and just talking about what is familiar on that page and what is unfamiliar on that page.
We get to see the ant walking again. That's familiar.
Friendly little ant.
We have X and Y axis.
Good. We've been seeing those graphs for a while now, and so they're at least familiar to us. Even if we don't necessarily understand them, they're hopefully becoming familiar. What else may feel familiar?
Well, I recognize down the right, those are, the coordinate graphs have an X and a Y axis. And I recognize some of the words, but that whole column looks a little scary to me.
So Janelle, let's talk about that, because it can, right? So this is a great example of where something can look really unfamiliar and really scary. But what is the instruction?
To trace the graphs.
to trace the graphs. So when we stop and read, and Leah and I were just talking about that, there's so many times where I'll ask her a question about an exercise, and she'll say, well, did you read the instruction? And she asked me something the other day, and I said, oh, well, look, there's the instruction. So we all do it, right? We all skip right over reading the instructions. But as soon as we read that instruction, does it feel a little bit more approachable?
Yes, for sure it does. I just finished this lesson with my 12-year-old. And yes, so we did do that. Then as you get close, okay, so we would just trace that horizontal line. It's dotted in the first square. Then we would circle, which is already helpfully there for us. Anyway, and then we would trace the solid gray line, right, in the second grid, and then the dotted line again, which is also, I see gray-ish, yeah, on top of the dots. I don't even know how to read those things. It doesn't tell me to read them, but like that, the words at the bottom.
So what are the words at the bottom on the
Well, the
first,
very, very
on that
bottom,
top
I
one?
shouldn't call it words. I was talking about the equation at the bottom, which is a little
Well, look in
fuzzy.
that first box, and what is the word that's in that first
Function.
box on the grid? Function. So
Function.
there's our function, and then we're given the symbols that represent that function.
Okay.
And then third box, what does it say?
The third one,
Yep.
it says no inverse.
Okay.
You're counting boxes. She's counting graphs.
I'm
Yes.
sorry. The derivative. It says derivative.
Okay. And then what does it say underneath that?
The slope of f of x equal to 1 is 0.
Okay. So is the graph the same as it was in the first box?
It is. Right?
Is
Yeah.
it exactly the same?
Well, it's not dot. It's not. Is this a trick question? Hang on.
It's not dotted, you're right.
Okay.
It's not dotted. Is it in the same place though? Or did it move?
Well, my resolution is not great for some reason.
Okay.
Maybe. Okay, no, because in the first one it's like y equals 1. Yeah, and the second one it's on the x-axis. The line below the x-axis is darker than the other lines on my second grid, and so that confused me. I see now that it's on the x-axis. Okay.
It's on the x-axis. So does that make sense when we see it says the slope equals 0? Does it make sense that that line would be on y equals 0 instead of y equals 1?
No.
Yes, although slope doesn't really matter where the line is, does it? I mean, slope to 0 could be anywhere.
Okay, so if the first line was the function and the second line is the derivative, it's a different line, right? Because the first line was y equals 1. The second line was y equals 0.
Okay.
And we're told the slope equals 0. So what might be true about the derivative and what the derivative is?
Somebody else's turn.
And it's okay. It's okay, right? It's okay. I'm just pushing you to like make guesses about things,
So
right? But the derivative is the slope, right? So we're saying that line is the slope of the function. And so the slope of that function is going to be 0 everywhere. And so that's why it's the line y equals 0.
But everything Chrissy just said is not what you're supposed to get from that graph.
No,
Right?
no. And I'm just talking about how you could play the comparison game with your 12-year-old.
Okay, right. Right.
And I do have a question, because I, oddly enough, also did this page with my almost 12-year-old today, just like about an hour ago. And I didn't get any of that discussion with him. But supposedly if we were going through this and just suppose this was the complex and we were doing this at home, some of those questions, would that be in the companion that I could see from that? Because I love math and I didn't really get that also because I'm I'm reading this off of my computer because the printed copy doesn't have a good resolution either. So I didn't realize that those were different lines either until we talked about it. But would that be something that I would pre-read and then I'd be able to explain it to him at home?
No, I don't, we don't really have that level of sort of guidance for you as a parent, but in the complex, there's going to be more in that left-hand box that's going to sort of help guide that right-hand box. And I think you're also going to notice that those right-hand boxes are going to be the same over and over again. Now, what you will find in the companion is a little video clip for the tops of pages 1 through 4. And so you can actually watch a little video clip of me walking through each of those boxes. And so it may not give you the questions to ask, but it's going to give you, oh, this is what they're doing in each of those pieces of it. So now I feel a little bit more equipped to go back and do that with my student.
Carrie, I really
Yeah.
appreciate those questions too, because it's once again the mimetic versus the didactic, and the point is to just copy until you have the questions. But sometimes you can ask questions like Kirsty was making mathematical connections, which you want to do, as soon as you can with your children. But also it's like, okay, look at the second box where we actually circle the answer for you. The whole point of that is scaffolding. We give you a question and circle the answer because one day we're going to give you the question and there's no circle. We just want, and it's all in that question will always be in that location. So as the children get older, they start to say, oh, I know what's going on. And that would be the same with all these graphs. These graphs, if you're in expressions, week 25, page 1, guess what the graphs are on the right? Exactly the same. So it'll come.
So let's talk about the big box to the left, where we have our ant. And let's first ask the question, which function are we examining there? And if you read the top line, it's going to tell you what the function is. So what function are we examining?
Is it the constant?
It is the constant function. Have we seen the constant function before?
Yes.
We have, right? So we've seen this constant function before. And the parent constant function is y equals 1. And so we're showing you there why that is. And so there we've got our ant. Which way is the ant walking?
To the right.
To the right. Do you think that's important? Why do you think we asked which way he was walking?
Because when we are determining if slope is positive or negative, we're going from left to right.
Right. So usually when we talk about our functions and we talk about the behavior of our functions, we're always going to talk about it from left to right, the way that we read. And so mathematically, we're going to say as x increases, what's the behavior of my function? What does y do? And so here's a great example of what Lee was saying, right? We're just asking the question. We're not making a mathematical understanding of it at this point. But what we're trying to do is help those students get really confident that they know when we're talking about a function, when things are happening, we're looking left to right, that we're always looking left to right so that they become, right, sort of conditioned. And then one day they're going to go, that's why we always talk about things going left to right. And so we're pointing out something here that maybe doesn't feel mathematical, but one day will become mathematical. So, and we already kind of talked a little bit about this, but we're talking about the constant function and what is the slope of the constant function? How does the function change as x changes?
It doesn't.
It doesn't, right? This is the bike path that we all want to be on, is our constant function, because its slope doesn't change. It doesn't go up, it doesn't go down. And so we say that its slope is 0. When we think about it mathematically or numerically, we say its slope is 0. Let's go ahead and look at the next page. And notice we're going to talk about the same question. We're going to talk about the function and the slope of the function. but I also really want to invite you to talk about what is familiar and what is unfamiliar on this page.
The ant is familiar and X and Y is still familiar.
And once again, the ant's going from left to right.
Good.
This time he's working harder.
Yeah, a lot harder.
The x delta x is still at the bottom of the fraction, and the delta y is still on the top.
Right. So we're starting to notice some formulas. That's excellent.
Mhm.
Now on the first page, that right-hand column felt very unfamiliar. How does that right-hand column feel now? Does it feel a little bit more familiar? Even if we're not sure what it means, are we seeing that there's a pattern?
The words are the same, and I now have a comparison that I can do.
Excellent.
This column actually looks kind of like this on all 16 pages in this lesson.
It does. How about if we compare the top box on the right to our big box on the left? Are they the same function or are they different functions?
They're the same.
They're the same. So we're going to be looking at 16 functions over 16 pages. We're going to be taking a closer look right on the left-hand side, but then we're going to be looking at all of these same ideas on the right-hand side. Are these functions, right, feeling familiar? Have we seen different functions before? Have we seen the function y equals x before?
Yes.
So I really want to emphasize that we came up with this list of functions and we keep looking at them again and again and again, right? So we looked at them in lesson 9. We looked at our constant and our line. In lesson 11, we looked at all of our functions. In lesson 13, we looked at the conic sections, but then we also said, hey, here's a whole list of the functions again and what they would look like in polar coordinates. In lesson 16, we looked at the trig functions specifically. And then in lesson 17, we looked at all of the functions again because we looked at how they might intersect with one another. In lesson 18, we talked about what it might look like to transform these functions. Now we're looking at them in lesson 25, where we're looking very specifically at the slope of the functions. We're going to look at them again in lesson 26. And then we're going to wrap it all up in lesson 30. We're going to have one more summary. So we're going to look at these functions over and over and over again through the course of the year, right? And then again and again and again over multiple years, so that hopefully by the time our students graduate, right, they're going to be able to sit there and say, I know what these basic functions are, what their graphs look like, what their slopes are, what the area is under them, how they might intersect with one another, how I can move them around in the coordinate plane. So I just wanted to point out, right, that we're seeing these same ideas over and over and over again because we keep going that little bit different. And so it's that idea of coming back and reviewing and going a little bit farther each time.
Are there
So
only 16? Is that the number of them? Like total? Seriously?
There's just 16.
Well, that's perfect.
It's like 26 letters in the alphabet. There's just 16 functions.
Really?
Now there's obviously a lot more functions, right? But these are the ones that we picked that make sense because we're using x squared to represent all of the power functions that have an even, like x to the 4th, x to the 6th,
right,
and so on. And then x cubed is kind of representing all of our odd power functions. And then we can sum, multiply, divide functions. We can compose functions. So we can make functions look really funky, but they all come back from being built on these 16.
So these are like the principal parts.
Yes.
Okay.
So what do we know? Looking at this again, so we're looking at our line, y equals x. What is the slope of the line, y equals x? And whether you see that on the page or whether you remember that from someplace else.
And the slope is rise
Fine.
over run. So we have
Yep.
1/1, which equals 1. So our slope of our
Excellent.
line is 1.
Is it the same everywhere on the line? Yes. Right. So it doesn't matter if I pick 2 points that are close together, 2 points that are far apart, 2 points that are really positive, 2 points that are really negative. It doesn't matter which 2 points I choose. I'm always going to find out that the slope, that the rate of change between them is 1. Let's go ahead and look at our next function on our next page. And what function are we looking at here?
The title is at the top.
Quadratic.
The quadratic, yes. Y equals x squared. So now I'm going to ask you, what can you tell me? You don't have to tell me numerically, but what can you tell me about the slope of this function?
Mm.
It's going to change.
Very good. It does change. How does it, in what ways does it change? Could you describe the change?
Well, if you were thinking of it in terms of a roller coaster, you might be going downhill very fast and then slowing at the bottom and then going slow uphill.
Good.
It's inverted,
So,
so that means it's mirrored imaged. It is
okay, good.
Symmetrical.
It's symmetrical. So when we're going down, what kind of math word might we use to describe the slope of something that's going down?
Negative,
Negative. And
Yeah.
how about something that's going up?
and then it becomes positive. At the origin,
Positive.
it changes and becomes positive.
Ah, it changed, right? So it was negative and then it became positive. What happens, do you think, right in between, right at the origin? What do you think the slope has to be between negative and positive? Any ideas? 0. Good. So there's exactly 1 point here where my slope is 0. To the left of that, it's negative. To the right of that, it's positive. And then Jill said it's not just constantly negative or constantly positive. It's actually changing from point to point. And it was a higher slope, right? A greater slope. It was going faster. And then it sort of slows down. It decreases as it comes into the origin. And then on the other side, right, it starts off slow, but then it gets faster as it's going up, right? The rate of change is getting faster as it goes up. So without actually putting numbers to it, we can look at a function and we can describe what's happening. So let's take all of those ideas and let's look at our next slide and our next function. Okay, and so what function is this one?
Cubic.
Cubic. And just to point out, on that the last slide where we were looking at x squared, right? We can think of that as like the goalposts, right? My ends both went up. And it's our representative function, right? So for x to the 4th, x to the 6th, x to the 8th, x to the 142nd, right? All of those are going to actually go, right? Both of my ends are going to be going up. Now, as my power gets higher, they get closer together, but that same general shape is going to hold true for all of those even powers. Here, we're using x cubed, and as we describe the slope of x cubed and how it changes, we can apply that to all of our odd powers. So x to the 5th, x to the 7th, x to the 193rd, or for Lee, x to the 37th. So who wants to take a stab at looking at our cubic function here and describing the slope?
It goes left to right.
Always going left to right.
So this one's always going to be positive because it is always going up, going to our side, except at the origin.
Right. What happens at the origin?
Well, we're going to switch over from being, well, it's cheating, but I know that the derivative of this is a parabola. So we're going to have that changeover like you do on a parabola going from left to right. So parabola is going to go from negative slope to positive slope. This cubic is going from being in a negative quadrant to being in a positive quadrant, and it reflects that at the origin.
Okay. So good. So it's going to be at the origin. It's going to be 0. It's always going to be positive. And you pointed out some things, right? So you were saying I can use my derivative to analyze this. And I don't think you used the word concavity, right? But we see where it sort of switches, right? So we were slowing down how, right? Our rate of change was sort of slowing down, and then it starts to speed up, right? And so that's that idea of concavity. It's slowing down, so it's concave down, and then it's speeding up, it's concave up on the other side. Right? So without actually putting numbers to it, we can look. I just want to encourage everybody that with your students, this is a fun game to play, right? Just draw some squiggles. They don't have to be perfect functions. They don't have to be like anything perfect, look out, right? So like I'm looking outside this window and I'm looking at cars going by and umbrellas and buildings and vans and manhole covers, right? And so pick any of those shapes and say, okay, well, if I put an X and a Y axis here, how would you describe the slope of these curves, right? Is it positive? Is it negative? Is it getting bigger? Is it getting smaller? And just becoming familiar with how we can describe just so we can become familiar with how we describe those curves is really going to set our students up to when, as they gain confidence and they start to calculate more with derivatives or calculate more with points and numbers, they're going to go, oh, now I see how those numbers are describing the things that I already knew, right? I'm going to give them a way to quantify things that they already know.
Christy, at what domain do they start calculating? Is it like transcendentals, or I kind of remember my college training, it's almost pre-calculus when they start doing it.
Yeah, so they would, but in the math map. So if we go back to the first page of this lesson, if you can flip back to page 1.
Yep.
Look down at the bottom. Now they're not actually calculating, right? We're kind of just tracing at this point, but that is the calculation of the derivative that our 6-year-olds are going to start practicing.
They'll start in decimals, Yaelin.
Okay.
Yeah. It'll be super simple numbers and it'll be all set up for them, all scaffolded. They'll just have to simplify the last step.
Okay.
So eventually they're going to be calculating on their own, and they're going to be applying some ideas that are a little bit more advanced. But one of the things that our tutors have discovered is that just challenge students love to calculate the derivatives of power functions. They feel so empowered, pardon the pun. So it's a process that any of us can learn, even if we don't really understand why it works and we don't really understand what we're doing. It's a process that we can do, and then we can actually compare that. So
so can I ask a question? So
sure.
the derivative of 2x to the 4th power is 8x to the 3rd power?
Yes.
Oh, okay. Okay, thank you. Okay.
And I'm sorry that I don't know everybody's name, but somebody just mentioned that she said, well, I know the derivative is going to be x squared. And so one of the things that our students are going to do as they get older, and again, right, so even in our Challenge A classroom, is they're going to look at those graphs of the function, and they're going to compare it to the graph of the slope. And they're going to do exactly what we just did. Oh, it's positive. Well, now look at the graph of the slope. Is it positive? It is positive. Right. So we're going to be able to look at those graphs and see, just for our own selves, we're going to go, yeah, that makes sense. That makes sense. These things all line up. So there's this opportunity to build memoria that's going to lead to a richness of understanding that I think most calculus students don't gain because they're so busy trying to calculate. And
I
so I
wanna-
just want, yeah, go ahead.
Okay, so I want to add some of like doing this at home at the table. A lot of parents are asking me about the time it takes, and it's wisdom on your part. So if I had 3 kids in front of me and I had the function week that we're looking on now, lesson 25, I would probably 1 hour of that week just say, everybody open up your books. Let's just look at the tops of the functions and look at 4 or 5 of them and ask these same questions on that day. And then it's just tracing for these little guys. Then they can go the rest of the week and work on their own on some of the problems. And the calculations, like you see below, are very scaffolded. So your middle school kids can go ahead and do the calculations and the tracing and the copying without you. So the thing that we want to see parents doing is that they get math confidence and they know that, look, if I just spend 1 good hour a day going over this concept with the kids, because it's mapped, it's all looks the same to all of us, you're going to be able to launch your children more quicker and to harder concepts than I think that you've been able to do before.
I just got to
All
add, the
right.
scaffolding is key on all that.
Mhm.
And I think that's where the beauty is here.
Thank you.
All right, so let's go ahead to our middle slide, if you could, Christine, and we'll just pause there for a moment and let everybody know that if you are all set for your 24-25 year and have access to week 7 of CC Connected, so that means you're a director or you have paid your tuition, you will have access to the Math Map Companion. And through the Math Map Companion, you have access to those digital resources that we are releasing. So that is live. We just continue to tell everybody it is very much an in-process product. We are doing our best to release a quality product, but we have really big plans. And so we're having to build that a little bit at a time as we go. And so we just want to let you know it's there. Please be patient and let us know if you find errors or mistakes or you have questions. Please certainly let us know. And then just a reminder that the early adopter sale is April 23rd through May 7th. And then one final note about the companion. I just want to say this, that it is there to support you as parents. It is not necessary. When Lee and I first sat down and talked about what this curriculum was going to look like, we talked about having a curriculum that was self-contained so that families who are doing life on the go, they're whether you're on your way to a field trip or you're going to take a meal to somebody who's sick, or maybe you're cutting grandma's grass and so you've got to travel to her house, whatever that is that life brings your way, that you have a booklet that has everything you need in it. It has the charts there that have your reference materials. You have the solutions guide there that have and more than just answers, but steps to solving problems. You've got a game, right? You've got all the different things that you need. And it is self-contained. And our tutors overwhelmingly said that the best thing to do was just to approach those booklets, enjoying the fact that they were self-contained and using the classical skills of learning that we've been developing, and that the companion is a nice support. But we really just want everybody to know that you don't have to be in it to be successful, that it is there as a support. There are extra resources. But those booklets really that is the curriculum, and it was specifically designed for you not to need to be in the companion all the time to help you do this. All right. Are there any questions before we look at lesson 26?
I just want to add, the whole reason Kirsty every week says familiar, unfamiliar is the first year through, that's your only job, is to figure out what do you know and what do you don't know. And then as you have time, go ahead and use those support materials. And then as you have more time, go ahead and use the companion. But it's expecting to know everything all at once is where you're going to get frustrated, and nobody does. Think of it as studying your Bible. I mean, how many times do you have to reread John 17 to know what in the world the Lord said? It's the same for all things where people are wrestling with information.
All right. So before we move on to lesson 26, I'm going to go back and I'm going to ask you a question. So lesson 25 was differential calculus. We were talking about the derivative. And the question that I kept asking you is, what is the function and what is its slope? So what do you think when we say derivative, what do you think that we're interested in about the function?
Slope.
Slope. Okay. So if all you came out of this week with is that derivative is the slope of the function, right? Even if you don't really know what that means, but if you have that grammar that the derivative is the slope of a function, right? You're doing well. So now let's go ahead and look at lesson 26. And you're going to see that I'm going to ask you the same questions on each of these pages. And let's go ahead and jump in with that question. I'm going to go ahead and I'm going to say, what function are we looking at? Is it familiar to you and why? And then we're going to talk about what the area is of the shaded region. So go ahead and talk about that for just 1 minute.
So what's familiar to you guys? What did we just look at?
The graphs.
And this particular one is the constant function.
And notice there's 5 graphs on the right again.
Mhm.
But one thing has changed. Step 2 is no longer asking you about the derivative of the function. Step 2 is now telling you the integral. So if you look down the line, this function, integral, derivative, inverse, and translation are the 5 questions you ask about the type of line you're looking at and how they relate to one another. So we give you 4 in week 25, and then we give you the 5th one in week 26. Okay. All right. Do you see
Where
the
is
ant? What direction is the ant going in? Left to right. It feels like overkill, but all of a sudden you're gonna have a child who's doing the calculations Yading asked about, and you're gonna have to say, remember, it's left to right. That's why your negative isn't correct or your positive isn't correct.
And what if the child asks me, Mom, what is C? Because he's just looking at integral and that's a new one. And then he goes, what is C? What would a parent say?
I don't know. Let's go find out.
From the companion?
Yes.
Well, the charts would be your you're not going to have your charts here, but your charts are going to be your best resource for that, because your charts are going to really clearly say that C is your constant of integration. And then you can talk to your child and just say, oh, wait, constant. Have we seen constant before? We have seen constant before. What does that mean? Right? It just means it's a number that's not changing. And so C just stands for constant. And even if they don't know what that means this year, right, you can just say, hey, it's a constant.
So when you say look at the chart, you're talking about the transcendental charts in the middle of the book.
Yes.
Yeah, I'm looking at it and it said, oh, there's a section called integration rule. And I said, oh, wow, C is constant.
Thank you.
Do you mind reading the way you would say that equation under the integral?
The integral of f of x dx equals x plus c.
Okay, so you just said dx. And then what about the derivative? How do you read that equation? Slope equals m equals, how do you say the next part?
I usually just say dy dx.
Where it's like an F and then an apostrophe or whatever.
Yeah,
that's just the derivative of f of x. That apostrophe just is the derivative of f of x.
So that's how you say it. M equals the derivative of f of x equals 0.
Yes.
Okay. See, I felt
and again,
that's empowering to know how to say that.
And
Go.
those notations are in the charts with how you read them.
Oh,
And
good.
then they are also in the audio glossary. So,
Okay.
yeah. So let's go ahead and look at our next page.
You know, you might want to be playing the audio glossary in your car like you do the timeline song.
Sounds good.
Is there going to be a CD coming out for that?
You're gonna have
It's
to
not that long.
So. But is it an MP3 file right now in the companion? Is that where it is, Kirsty?
It is, yes. Okay, if we look here, is anybody surprised that the next function we're looking at is y equals x?
No.
No, right? That's what we looked at last week, right? In lesson 25, we went to constant, and then we went to y equals x. So here's a question: is the area, if we remember back to the last one, our area, was it an exact area? Could we calculate that area on our last page?
No, we didn't talk about it.
Oh, it was a rectangle. Could you calculate the area of a rectangle? Yeah. On this page, what kind of a shape is the shaded area?
Triangle.
Triangle. So do we have a formula? Could I calculate the exact area of that triangle? Yep, I could, right? So I could estimate it, but I can also calculate it exactly. So what would the area be? Who wants to say what they think the area is?
Eight.
8, right? And if we were to calculate that, we could say, well, if x is 4, its base is 4, y equals x, so y equals 4, its height is 4, so 4 times 4 over 2 equals 8. And that matches what we are adding up if we were to count up all of those squares and triangles. So that feels pretty straightforward. Let's go ahead and look at the next slide. Okay. So what function are we looking at?
Our quadratic function.
A quadratic function, right? So if you're playing along at home and you were writing out all of these functions, you might notice that we went from y equals x to the 0, the 0th power of x, then y equals x to the first power of x, then y equals x squared, the second power of x. Right. So we're moving through that way. And so as we look at this one, what shape is underneath is that shaded area?
It's approximately a triangle.
It's close. Is it exactly a triangle? So does anybody have a formula for a shape that has 2 straight sides and a curved side? We don't, right? It's kind of an odd region, and we'd be like, we don't have an exact formula for that, but we could estimate it. And so if we were to estimate that shaded region, what would we come up with? Anybody want to take a guess at what the estimate would be?
3.
About 2.5 or yeah. Oh, 3. Yeah, 3.
Okay.
And it's okay to be wrong. It's just not okay to say 30. Right? But it's okay to say 2 to 3. So in helping our children just, estimate, which is of course calculations or calculus is where we go into the exact numbers, but you're still really estimating with every single problem. It's rare you get an exact shape that you can match up.
Lee, that's so important, isn't it? Because when we blindly calculate and we don't have a sense of what the answer should be, right? We're really at the mercy of our calculators. We're really at the mercy of, what somebody else is telling us, versus having confidence that the answer we're getting is accurate, because we can look at that and Lee's like, well, I know it's not 30. So if I had calculated 30, I know I've made a mistake somewhere. And so that's one thing we really do want to help our students recognize the value of being able to look at things like this and estimate what it actually is. So this is where the integral calculus comes in. And I'm not going to get too deep into it, but what it's like is if you think of a loaf of bread, and I'm going to talk about volume just because it's easier for us to think sometimes in terms of 3D, right? We know that our bread, maybe if you make it at home, right, it may have a very irregular shape, right? Some people make beautiful loaves of bread that are just perfect, but most of us, right, when you put your loaf, whether you put it in a pan or whatever, it comes out a little bit irregular. If I was to slice it up, can I get to where each of my slices feels a little bit less irregular, where my slices are maybe along the top, they're straight instead of bumpy? And so if I looked at each slice, I might be able to find the area of that slice more easily because that slice may be a nice regular shape that I could estimate. And then if I add up all of my slices, right, what does that look like? The whole thing, right? And so that's what we're going to see as we move on through the domains with integral calculus is we're going to start looking at what does it mean if I slice this area up? So all told, I see a curve. But if I was to zoom in, I might get to a point where each individual little piece looks a little bit straighter, right? Those sides look a little bit straighter. And so now maybe I can say, okay, well, what if I was to estimate, right, with rectangles or trapezoids? And as I get narrower, my estimates are going to get better. And so that's where we're pointing students to. So if you look at the charts, for those of you who already have them, you're going to see that we talk about something called a Riemann sum. And that's what we're going to end up building towards, is helping students to get this sense of slicing this up. And that's where our title, accumulated change, comes from. Because we're going to say, well, if we slice this up and we find the area of this slice and we add it to this slice and this slice and this slice, we're eventually going to get the whole. Okay. So let's go ahead and look at our next. And here, if we were to calculate this, just for those of you who are curious, our integral here would be x cubed over 3. So at 2, it's going to be 8/3. So notice that's right between 2 and 3. So if you were between 2 and 3, you were spot on. So let's go ahead and look at our last page. Right. And are we surprised? Are we finding rest that we're looking at y equals x cubed? So we're seeing this pattern. And again, right now we're looking at this tiny little piece of area. What do you think the area might be there?
A quarter.
A quarter.
And as you can imagine, for the youngest children, we gave them answers. But for, once you get up to fractions, they're supposed to estimate themselves.
And so here's a great example, right? So if we were to go to x squared, right, we can't even really fit all of that area, but we're going to be adding a lot more area, right? Between 1 and 2, there's a lot more area than between 0 and 1. So that's something you could do with your students when you're looking at these curves to say, okay, well, is there more area between 0 and 1 or between 1 and 2? How about between 1 and 2 and 2 and 3?
Or
and
even
you can start thinking,
or even say 1 to 1.5, so that they don't go up to infinity.
this is true.
Mm-hmm.
So there's a lot of things you can do to help your students estimate. And so here's the question for you. This lesson is about integral calculus. We've been looking at each of our functions and we've been estimating area. So what is the integral all about calculating?
Area or
Area. Yep. So there's our big ideas, right? So when people hear calculus, some people go, oh, I love calculus. Some people go, I hate calculus. Some people go, I never did calculus because our society has decided it's a gatekeeper and they never let me through the gate. But now, hopefully everybody on this call goes, well, wait a minute. I know that the derivative is all about slope and the integral is all about area, right? There is the big idea behind calculus.
It's
Now,
just,
here's the really cool thing. Oh, sorry. Go ahead, Lee.
oh, so it's just that what's so great about Leibniz and Newton is they recognize hardly anything straight. So they figured out a way to do it with curves.
And speaking of them, that's what I was just going to say is that you had, if you go and you look at the history, right? So if you're a history person, you go and look at the history of calculus, it's really fascinating because you had Leibniz and you had Newton, and they both were developing calculus independently. And so that's why we kind of have weird notations, because we adopted notations from Leibniz and we adopted notations from Newton. We brought them all in, but they came up with the same idea. And then they both came up with the idea of differential calculus and the idea of integral calculus. And the amazing thing is that they were developed independently to answer different questions. And then they discovered that the two things are essentially inverses of one another. So if you take the derivative of the integral, you end up with the function. And if you integrate the derivative, you'll end up with the function, essentially. And so, but the two things were developed separately. They weren't developed together. And then they discovered that, right? And so it's just one more piece of evidence, right? That mathematics isn't man created, that mathematics is God created, and that we are discovering his truth that he's revealing through mathematics. Because I just think the story of how calculus was developed is just fascinating. So anyway, lots of fun to go and research if you have a history bent.
So I wanted to add too, that ties into what she just said, is the whole time I've been developing week 25 and 26 and then checking the work and doing it for all 13 or 12 or 13 domains, is I don't do lesson 25 and then 26. I open them up and do them side by side. And so that's something like if you have a child that's maybe flying through it in, say, the fractions year or the complex year, tell them after they get through 25, 26, do them again next to each other and see what they see that's familiar and unfamiliar between the lessons, and let them start to discover that the graphs are the same in both weeks and that the derivatives are the slope and those kind of things. It's just one more way to use the book rather than let the book use you.
Well, that brings us to the end of our lesson pages. So are there any questions before we finish up for today?
Do you mind telling us how to read the bottom part? Like how would you, those things where it says subtract?
Your translation?
Sure.
Or you
Okay,
mean the
so
subtract, gotcha.
Sure. Those are definite integrals. And so you would just say the integral of 1, and I can't actually see the numbers. Let me see if I can zoom in my screen. I can't. I'm on my phone. But it would be the integral of 1 from 0 to 3 equals x evaluated between 0 and 3, which equals 3 minus 0 equals 3.
Did you see how I snuck in subtraction practice? Because I don't expect any of the kids to read that, but I want a parent to see where they're going with it.
Right. But it really is empowering to know how to read things.
Mm-hmm.
So along with that, I have the complex. So I'm reading that in a complex level, you are in the instruction, there is shade the Riemann sums. And scaffolding is important. So for the Challenge 8 parents this coming year, this is going to be the first time seeing Riemann sums probably. And so how would you advise these parents that they don't have the scaffolding from before?
But they do. They can go online and look at naturals. They'll also be able to look at integers and fractions, and then they'll be able to look at the charts in the companion. There should be enough things there
So
to catch up where scaffolding's missing. That's
Yeah.
why we're releasing the early
And the
grades.
charts again, yeah. And again in the charts, right? That those charts are in every single one. So for that parent that goes, okay, wait a minute, I haven't heard of Riemann sums before. They can go and look in that chart and read about them and see examples of where they're going. So they can go back, as Lee said, and look at those earlier lessons that we've released digitally, but they can also look ahead at that chart, and then the companions there if they want to dive in even farther.
Okay, thank you.
Riemann Psalms, you're funny, Jenna. Okay, so listen, here's the big takeaway from all this. Most of you here have read Carry On, Mr. Bowditch. And when he decided that he wanted to study this level of mathematics, you'll remember he had to teach himself Latin first because all the math was in Latin. Then he had to do what we're doing. So we are crippling you by not making this in Latin. So at least please do the work that it takes to get it done in English. Oh. I'm glad you're not feeling crippled, Alyssa.
All right. Well, thanks everybody for being here, and approaching these big ideas with us this week. And next week, as I said, we'll be using our imaginations. We're going to be talking about NB and what that means in the math map and in general, and looking for patterns. And we're going to be looking at those patterns both symbolically, and we're going to be looking at patterns in words as we talk about proofs. So come back next week and bring your imaginations.
Thanks so much.
Thank you.
Thank you.